So this is another really good word problem for thinking about what you're doing. This is going to involve something that has 2 units, and we're going to be, it's got 2 steps we're going to be thinking about. So the first is part A, and it says solve the density like a unit conversion problem. So that means that we're not going to use D equals M over V. I suspect a gas station is watering down their gas. I took a scale with me and measured out 1 gallon of gasoline. Notice that's a volume. Its mass was 7.1 pounds. Here's one conversion in here already, but of course you could have gotten it from this chart. You're going to need another conversion in here too. You'll see that's why I posted the chart. Question is, what is the density of the gas at the gas station? So if you were to do this, D equals M over V, you would know that you needed your mass, which is right here on top, and your volume on bottom. You can also just use the units. So it's asking grams over milliliters. It wants to know what those are. See it right here? What is the density? So this is telling us we need some kind of a mass on top and that we need some kind of a volume on bottom. So we look right, where's our mass? Here's our mass, 7.1 pounds. Pounds are a type of mass. Use a scale with it. And then volume, here's, over here, here's our volume. 1 gallon of gasoline. All right, so now we need to do a conversion. Let's get rid of our pounds first, because those are a nice normal diagonal. And notice over here, where is he? A pound to a gram. So we can do that conversion. And then I'm going to put a gram. I'm automatically putting a, well, do I need a gram down there? Actually, look, I've already gotten what I need my top unit to be. So I want that one. I don't want to put it down because that'll get rid of it. And I want to keep it because that's what the problem's asking for. So we're good to go on our pounds. Now, remember, you can do any diagonal. It's just kind of weird feeling. So we're going to take this one up to the top, gallons. And here it says we can go from a gallons to a liter, or in the problem. And this one's it in milliliters, though. So I need to do one more step. Again, I throw the liters up because before I even think, and then I'm like, yeah, I can take it to milliliters. So you'll notice my gallons are a diagonal, so they'll cancel. And then my liters are a diagonal, so they'll cancel. So I'm just going to throw my numbers in. 453.6 in 1 pound. 3.785 in 1 gallon. And 1 times 10 to the minus third liters. I'll just throw that in a calculator. 7.1 times 453.6 times 1, exponent key, -3, divided by 1, divided by 1, divided by 3.785, and divided by 1 again. Enter. So that gives me 8.5 times 10 to the minus 1. We'll double check them for sig figs here. This is 1, 2 sig figs, 1, 2, 3, 4 sig figs, 1, 2, 3, 4 sig figs. So looks like I need to go with the 2 sig figs. This one is exact because it's all in the metric chart. So I'm good to go on here. As a little note on this next question, not this next, but this question has 2 parts. So if gas has a density of this value and water is more dense, is my gas watered down? So I'm going to put this part A, I'm going to put this into a format that kind of compares it better. So 0.5 grams per milliliter versus, I can just move that over so I don't have the 10 to the 0.85 grams per milliliter. Because of my pounds canceled, my gallons canceled, and my liters canceled. Those are not the same numbers. This is the thing about density and it being a property. Regardless of how much you weigh out, it's always going to have the same density. A little bit versus a lot bit, it's got the same density at the same temperature and pressure. So right here, this 0.85 grams per milliliter, that is a larger number, which means that these are not the same. And if water is more dense, yeah, it would make sense that this is a bigger number and that, yes, they are watering down my gas.